Afternoon, everyone, and welcome to the EOL seminar. My name is Vanda Grubisic, and I usually don't announce our seminars, but this is a special occasion. Our seminar coordinators are on their PTO on leave, but the special occasion is actually to being able to welcome my PhD student, former PhD student, I guess, well, my PhD student, always my PhD student, right? Eva got a degree with me, working with me, but her degree, PhD, is from the University of Zagreb. She actually came to work with me in T-Rex, and we continued this sometimes in the same place, sometimes remotely, and she did a very nice job on her PhD. That was in 2010. She also holds a degree from University of Zagreb, Master of Science, and a Bachelor of Science from the same university. After her PhD, she moved on after some persuasion. I persuaded her actually to take a leap and go to the University of Innsbruck. And she worked there with Matthias Rotach for 4 years, working intensely on the infrastructure for boundary layer measurements in complex terrain. Those of you who have been in Innsbruck know the real meaning of complex terrain. And I look forward to hearing on some of that work. She came to us from Utah, where she is right now working with Dave Whiteman, analyzing some of the data from the Metcrax experiment for all EOL people. We supported 2 phases of that experiment in a beautiful natural valley, natural environment of a crater. And I don't know, maybe that will be part also of her talk today on turbulence characteristics of downslope flows in mountainous terrain. So welcome, and the stage is yours, Eva.
Thanks, Vanda. Thank you, everybody, for coming. I would like to acknowledge my co-authors. So apart from me, the research I will be showing is partly done with Matthias Rotach. Vanda already mentioned it's these measurements that we have in Innsbruck. And then part will be really on Metcrax, so I also want to acknowledge Dave Whiteman and his contribution. So, as Vanda already mentioned, for my PhD, I kind of did mountain waves and rotors, and then I went to Innsbruck and I switched to boundary layer. And I always somehow wanted to combine these 2 subjects. So I will be kind of talking about the turbulence characteristics close to the surface in mountainous terrain, but looking at different flow types that we might have in such a terrain. So we know that flows in the mountains are complex. I mean, it kind of goes without saying. And the complexity stems from different reasons. First of all, we have the terrain itself, which is very complex. Usually it's not an isolated mountain or an isolated bowl-shaped crater. Usually you have multiple mountains, multiple valleys, side valleys, all kinds of stuff. Then we have the flow that goes over the mountain and is affected by the mountain itself. We have downslope windstorms, mountain waves, and stuff like that. And then we have the boundary layer itself, and we know that boundary layer is quite complex, especially if you go to non-idealized, horizontally homogeneous terrain. And within this boundary layer in the mountains, we also have flows developing that are very specific to the mountain systems. So we kind of know relatively a lot about mesoscale aspects of what's happening in the mountains, like, for example, downslope windstorms or thermally driven flows. But what has only now been starting to do is, like, we want to combine and look at the interactions between the coupling terrain, the mesoscale flows, and the boundary layer effects. And it's still kind of far from where we want to be. If you, for example, see the figure I have above, so this is sensible heat flux for a series of days measured in different parts of the Inn Valley in Austria. So the black lines are measurements, and the pink lines are what you would see with a 2-kilometer operational model. And you can see now this blue square is what's happening under low synoptic forcing. And if you compare the 2 lines, I would say that they fit quite well. I mean, like, surprisingly well for a 2-kilometer resolution in such a complex terrain. But then if you go to a period which is strong synoptic forcing, it's Föhn winds, I will be talking about them later, you see that especially during nighttime, we have like quite horrible agreement between the measurements and the models. So there are still quite a lot of challenges of forecasting near-surface characteristics in complex terrain. And it appears that the forecast will depend on the flow type itself. So what I will be looking at are two extreme ends of the spectrum. So in mountainous terrain, based on generating mechanisms, we can have thermally driven flows which happen when you have low synoptic forcing. So they can be up and down valley or up and down slope, depending on where you are in complex terrain. And there have been studies dedicated to this type of topic for decades. I'm just mentioning here really just randomly a couple of studies. So they span really long into the past, at least for the general characteristics. And then on the other end of the spectrum, when you have a strong synoptic forcing, you have a very strong gradient across the Alps or a mountain barrier, you have the development of dynamically driven winds like Bora winds or Föhn winds. And they are, again, relatively well studied. There are quite a lot of theories, linear theories, there are quite a lot of mesoscale modeling studies, etc., like on the mesoscale characteristics. And there are also studies of how a boundary layer would affect this kind of flows, but there aren't many studies that study the opposite, like how these flows would affect the boundary layer itself. So I will be focusing in this talk only on the night time to make things more clear. Let's just go that way. So as I said, thermally driven flows, I would define them as downslope flows in this case, because I will be looking at what is happening on a slope. Downslope flows that develop under low synoptic forcing. You have a temperature deficit at the surface, and because of a difference between the temperature and the slope, and in the valley, like a valley atmosphere at the same height, you have a development of a baroclinic circulation, which drives the wind to go down. They're usually characterized by a low-level jet and very strong stratification close to the surface. And they're generally assumed to be a result of warm advection, because if you have stable stratification, that means that the potential temperature is increasing with height. So if an air parcel is going down, it will be actually warmer than the one that we find down. So there have been some studies about the turbulence characteristics of these flows, and the most recent one was by Grachev et al. They were studying katabatic winds in Utah in Matterhorn experiment, and what they observed, they were observing these katabatic winds with the jet maximum of about, I guess, 3 meters, and what they saw is that below the jet maximum you have negative momentum flux, and at the jet maximum 0, and then above it's positive, which makes sense because we have this shear that is positive below and negative above the jet maximum. And then what they also observed is that along slope heat flux is positive below the jet maximum and negative above, which would, I know that heat flux is not the same as advection, but in a theory, like if we're talking that katabatic winds are warmer advection, this kind of goes in line with this view. So we have like a warmer air being transported by turbulence below the jet and like colder air above. He also looked at scaling. So in boundary layer, we always try to find some similarity theory. We try to scale something so that we can apply the same results to other places and other types. And they found quite good agreement with what they would find over flat, horizontal, homogeneous terrain. Now, there was a recent study by Oldroyd, and they have a very steep slope. They have a 40-degree slope, and they have katabatic winds there as well. And they found that, well, not everything is the same as when you have this kind of a low slope. And I think that at Grachev it's like 2 to 10 degrees, so not very steep. Then on the other end of the spectrum, as I said, are dynamically driven flows, and what happens is they form in stably stratified environment. We have air going over a mountain and being displaced by the mountain is accelerating downstream. There are different types of downslope windstorms. The one that I'm showing on the left side is a schematic of Föhn winds, where generally one can apply shallow water theory. So you have this layer of air that is accelerating downwards. It's very turbulent, and it's warm. So it's warming of the air. And then on the right side, I'm showing a photo from Owens Valley in California. This is also a downslope windstorm, but on top of that, there's an atmospheric rotor, which is forming here, and it's very turbulent. So, as I said, we know quite a lot about the mesoscale structure of this type of flows, but from the turbulence perspective, there have been very few studies. There were some studies on what the TK budgets and TK characteristics look like. There were some studies about whether we can even apply turbulence measurements in such complex environment. And there was a study in Innsbruck, actually, during the MAP project, where they were measuring with an airplane, and they noticed that they had very negative heat fluxes in the middle of the valley of like minus 90 watts per square meter. So kind of the questions that maybe I want to answer are, okay, so what is the turbulence structure on a slope, and how does it depend on different flow types? Are there similarities between these flow types, or will they be very different? How does the slope angle actually influence this turbulence structure? And then, is there some kind of interaction between these two very different types of flows? And thermally driven flows are generally considered to be very weak and very sensitive to the large-scale forcing. And then I will also look at what is happening along a slope. So I want to see if it's homogeneous or not, and what are the sources of heterogeneity, if there's some. So I will kind of divide my talk into three main parts. The first, I will talk about flows on a shallow slope, and this will be most of the results from Metcrax. Then I will talk about flows on a steep slope, which will be most of the results from Innsbruck. And then I will talk about flow variability along a steep slope, which is, again, the results from Innsbruck. So Metcrax, for those who don't know, was an experiment that took place in the Meteor Crater in Arizona. There were two phases. I will be talking about Metcrax II, which took part in October 2013. So it was a big campaign. Mostly it was focused on what's happening inside the crater. They noticed that there are some warm and cold air intrusions and stuff. So there's really a bunch of instrumentation all around the crater and inside the crater. But what I will be focusing on is actually the tower, which is like this orange dot here, which was outside of the crater on a very large mesoscale slope with only 2 to 3 degrees. So it's not very steep, it's very large. The mountains are about 100 kilometers away, and the tower itself was 50 meter high and had 10 levels of sonic anemometer, so like a really nice data set. And it was located also 1.6 kilometers away from the crater, so we generally assume that it's not influenced by the crater rim. The dominant flow direction is actually down this slope, although there are other flows as well, and I'm just focusing on this sector that is down the slope. So on the other hand, we have the I-box, which is short for Innsbruck Box, and that's what I've been working on for 4 years. So it is a platform for studying turbulence in mountainous terrain and combines long-term measurements. And at the moment, we have more than 3 years of data with high-resolution modeling. So the location is this orange square. This is the Inn Valley in Austria. So you see it's really complex. There are like all these mountains around. And this right figure is like a topo map of our 6 stations. So we have 6 turbulence towers, and they're kind of, there's not put in a transect or in a certain orientation. They're put on representative surfaces. So we wanted to have a steep slope, a not very steep slope, a valley bottom, a mountain top, so, and etc. So we have this kind of like turbulence measurements and also remote sensing. And this is just like a view of our towers. Mostly they're just a single level towers, except for 2 locations where we have multiple levels. So I will be talking about the steep slope, which is located here. It's 27 degrees steep. It's facing north, which means that most of the time, especially in winter, we have these drainage flows developing there. It's not very long, it's only 250 meters long, and it's located 400 meters above the valley floor, which means that when we have nighttime down valley flows, they are not affecting this slope because they're not as deep as that. And mostly I will be focusing on 2 months of data when we actually had additional stations along this slope, and you can see them here on this Google Maps image. The little squares are the locations of the stations, and the white contours are the footprints that you would see from the stations if you had drainage flows. And I know that one is not really supposed to apply a footprint model in really complex terrain, but that's the best we can do to kind of get a feeling of what are the influences on our measurements. So this is kind of like a schematic what the slope looked like with these additional towers. And they were not very far apart, like 55 and 75 meters. So we expect there not to be much difference between them because it's such a short distance. We had a sonic on them and some additional measurements. And this is kind of a cross-section of what the slope looks like. So you can see that it's not really it's pretty flat, but not totally flat. There are some undulations, and they're on the scale of like 3 meters over a 10-meter distance, so kind of like slightly undulating slope. Okay, so first I would like to talk about turbulence characteristics on a shallow slope. So 2 to 3 degrees, and that will be the data from Metcrax. As I said, Metcrax is on this large mesoscale plane, and most of the time in this 1 month, it was like, I don't know, 90% of the time, we had the drainage flows developing, which had jet maximum between 20 and 40 meters, which is quite deep, actually. Grachev had only 4 meters, if you remember. So they're developing most of the time. And what they're characterized with, so this would be the wind speed as a function of height. This is the friction velocity, the heat flux, the vertical heat flux, well, slope normal heat flux, and this would be a long slope heat flux. So we see that below the jet, we have some friction velocity. So we have, if I would have plotted momentum flux, we would have had like a positive momentum flux and negative below and positive above, but above the jet, it gets kind of very low. The flow is quite stable below the jet, and then it gets quite neutral above. And the same as in Grachev, we have a long slope heat flux below and the negative above. So we can see that even though here we have kind of a different slope angle than what they were doing in Matterhorn, and our flow is much deeper, we have some characteristics that look very similar. So we can say that it kind of conforms to what they found. But then some of the times, and this was particularly on 3 nights, we had these very deep flows. So they were deep because the jet maximum is above the tower height. So I know that there are other instrumentation that was employed there, and there were LiDARs and stuff, but I haven't had time to look at them. So I don't actually know where the jet maximum is. That's why I just call them deep flows. And the question is, are they just deeper katabatic winds, or are they something else? If they're deeper katabatic winds, we then expect that they will behave the same as a katabatic wind would behave below the jet maximum, right? So, so if we look at the turbulence characteristics, we see, first of all, that the friction velocity, which is here, is quite high, and it's very constant with height. The flows are very stable, so if you converted this from kinematic to dynamic heat flux, it would be like minus 60 watts per square meter, while previously we were talking about like 10. And then they are all have a positive long slope heat flux. So at least that part would kind of fit with the katabatic theory, but the rest, I would expect the jet maximum to be somewhere around the height of the topmost level. So I would expect my friction velocity to be decreasing with height, because at the jet maximum it has to be 0 or very low. So it doesn't really fit with a very deep katabatic flow. The question is, well, what is it then? If you look at the budgets, so the above figures will be for the shallow katabatic flow, and the lower would be for these deep flows. And here is the TK budget, the budget of the slope normal heat flux and the horizontal heat flux. And we can see that in both cases, the TK structure is mostly dominated by shear, which is this line, and dissipation, which is this blue line. The momentum budget between the two is different. So we see that the gradient production, or destruction actually, is dominant below the jet, and here it's dominated throughout the whole flow except for here. And for the shallow flow, we have a significant contribution of buoyancy, while here, buoyancy doesn't play a role at all. And then for the long slope heat flux, it kind of looks similar. So close to the slope, we have turbulent production and shear production, and the turbulent transport kind of appears to be playing a little role, but not totally. So both of these heat fluxes are not really closed. The budgets are not really closed because, unfortunately, I cannot calculate all the terms. But we can see that there are some differences. Now, I can calculate something that is called the multi-resolution flux decomposition. So what this means is you take your data series and you calculate your flux, and then you divide it in half, and then calculate the flux over the two parts, and then cut it in half. So this way you're getting the flux at different scales. So here I have the time in seconds, and here I have the contribution of my flux. So if I integrated all of this, I would get the total flux. But this way I can see which scales, and this is time scales, my dominant flux is appearing. So above here, it's the shallow flow, and this would be the slope normal heat flux, and this is a long slope heat flux, and then the same thing for deep flow. So what I can see is this is the lowest level, and this would be the highest level, and then the colors go from like darker blue towards red as the height increases. So I can see that the largest scale of my flux is actually found at the surface, and then the time scale is decreasing as I go up to the katabatic jet, and then for the heat flux, the sense of a heat flux, it's like the scale are very small. For the long slope heat flux, again, the largest scale is at the bottom, then it's decreasing as I go to the jet maximum, and then above the jet, the turbulent contribution is really low, but there's a huge contribution which would be kind of from mesoscale, which would mean that there are some really large eddies that are contributing to what is happening to the heat flux above the jet maximum. For the deep flows, first of all, what you can notice is they're quite nicely separated. So the smallest scale is at the bottom. Sorry, where is my cursor? Is at the bottom, and then it's nicely increasing as you go up. And the same is happening here as well. So I was thinking, okay, this is time scale. What I'm actually interested in is spatial scale. And I can press my thumbs and believe that I can employ frozen turbulence hypothesis, and I can multiply my time scale with the speed of wind speed at each level and get from a time scale to a spatial scale, which will tell me, okay, how big is actually my eddy in space instead of how big is it in time. So if I do that, this is what I get. So for the shallow flows, now the maximum below the jet is pretty constant with height until you hit the jet maximum, and then above it's low anyway. So it appears to scale really well, and I can say, okay, my jet is kind of determining the size of these eddies, and it's just like one eddy, and it's determining the fluxes below the jet. If I do it for the deep flow, it totally doesn't help. It looks even worse. So for deep flow, the height at which I am will experience different sized eddies. And this is what you would expect for normal boundary layer, like if you were on flat terrain. So this kind of would tell me that the height is a really relevant variable for the deep flows, which means I would expect that the scaling and scaling over flat terrain is a function of z over L. Z is the height, L is the book of length. So the stability is a function of height. I would expect for the deep flows that scaling, or the same as over flat terrain, kind of applies, which of course I can try and see if this works or not. So here I'm showing on the upper part, it's non-dimensional wind shear as a function of z over L, so height over a book of length. And below, I'm showing the standard deviation of vertical velocity divided by friction velocity, which again is a function of z over L. So I know what it's supposed to look like over flat terrain, and these are these black lines. And then my data are plotted here, and I divided the shallow flow as below the jet and above the jet, because I expect this to be very different. So what you can see if you just focus on the upper picture is that below the jet, it kind of looks like it's falling on the line, not exactly. Above the jet, it's all over the place. There's a huge scatter. You can see that it's a log-log scale. So there is, like, the data are not conforming to what you would get over flat terrain. But then if you go to deep flows, it looks really nice, right? So as I mentioned before, I would expect that horizontally homogeneous scaling would work for these deep flows because they show this dependence on height. If you look at the lower row of figures, you can see that the same is true for sigma W over U star. I mean, there is quite some scatter here, but generally they fall on this line, kind of around the line that was determined in Kansas, which is quite flat. And then above the jet and below the jet, they just don't conform to what you would expect. And maybe just as a reminder here, because you might notice this later, the deep flows are much more neutral than the katabatic winds, despite the fact that they have a very negative heat flux, but because the friction velocity is so strong. So as a conclusion to the first part, we saw that shallow katabatic flows kind of behave as one would expect. They're mostly dominated by shear production and dissipation, the turbulent structure. The heat budgets are not closed, and buoyancy plays a part. Eddy size appears to be constant over the height of the jet, and scaling shows some conformity, but generally doesn't really work. The scaling is in horizontal homogeneous. So we can say, okay, we have something that's obviously dependent on a slope angle, and this is something we are not taking into account in our scaling, so we don't really expect it to work. But we can always try. For deep flows, they show quite a lot of differences from katabatic winds, and they appear to be not so sensitive to the slope angle because they appear to behave more like flat terrain flows, which we show, like we saw from scaling. Buoyancy is insignificant, have very large negative heat fluxes, strong turbulence, positive along slope heat transport, and I'm asking myself, could it be that they're actually downslope windstorms? Because Lawton noticed that there are these very large negative heat fluxes, and there are kind of some similarities from what we would expect for downslope windstorms. But then again, closest mountains are like 100 kilometers away, so can we still expect this downslope windstorm, which we know how it's supposed to behave close to the mountains, to maintain its characteristics so far away? So now I move to Innsbruck. It's all more complex. It's more steep. The slope is 27 degrees. I'm sorry, it says Metcrax. It should be iBox. So the nice thing about Innsbruck is we have a wind system called Föhn. It's dry and warm downslope windstorm. It occurs really regularly. It gets really warm, and it's been studied there for like 200 years. So we know really a lot about this kind of wind, and also we can forecast them and we can diagnose them, which makes things really easy because in Metcrax I have to guess, like, well, I think this is a downslope windstorm, and here I know because I know what are the characteristics of Föhn winds. What makes it nice and challenging is the fact that both Föhn, which you see here, okay, I don't know where my here has the same orientation as what you would expect for katabatic winds. So it will flow from the same wind direction. So now is the question, okay, can I actually tell them apart by their turbulence characteristics? And I will be focusing on 2 episodes. So I will be looking at quiescent conditions where I expect drainage flows to develop. Then I will look at the weak föhn episode where there was föhn on the slope, but there was a cold pool in the valley bottom. So at the valley bottom, we just didn't feel any föhn, which you can see here. Just a second, where is this? Oh, yeah. You can see here, this is the wind speed. On the slope, you have this is nighttime. You have kind of like high wind speeds, and on the valley bottom, it's like almost 0. And then there's this strong föhn episode where all of a sudden, the wind speeds just like go up. Unfortunately, it's not as high as one expects, like for example in Boulder with the Boulder windstorm, but it's still quite high. So if I look on the slope, I can distinguish these 2 types. One is the low synoptic conditions katabatic winds, and this will be this darker line. And the other one, the red line, is föhn, and I know it's föhn because we can diagnose it in Innsbruck, and I know it should be happening here as well. So what you can see, if you just look at the black line, is we have a shallow flow with the jet maximum at, well, between 1 and 2 meters. So quite far from what we had in Metcrax, which was 20 to 40 meters. The friction velocity is quite low. The heat flux is quite low. It's decreasing with height, which was similar as in Metcrax. But the thing that is totally different is that at the jet maximum, we have a very negative along slope heat flux. In Metcrax, we had 0 heat flux, and we had positive below. So this would mean that this type of katabatic wind, instead of being warm advection, is actually cold advection. And doesn't really make a lot of sense, because if your slope is steeper, you would expect your certification to have an even larger influence in retarding the flow. So if we compare it, as I said, to Metcrax, so the wind speed, well, the form doesn't really look similar, but there are some similarities, except this along slope heat flux, which is like exactly the opposite. Now, if you look at the red line, we have deeper flow. We don't know where the maximum is. The friction velocity is much larger. It's increasing with height. The stability is, the heat flux is much lower. It's about minus 60 watts per square meter at 1 meter above the surface. So like really negative heat flux is very close to the surface. And then the long slope heat flux is kind of around 0, and it's becoming positive. So if you compare it to Metcrax, we have this kind of tendency to have positive values, not really very close to the surface, but we have kind of very negative heat fluxes, large friction velocity, and kind of a similar profile. So that would tell me that what I saw in Metcrax really is a type of a downslope windstorm. What about the budgets? We saw that in Metcrax, the TKE budget, which is what I'm showing here, was pretty much just dominated by shear versus dissipation. And here, for both flows, and here for the katabatic winds, here's the shear, here's dissipation. First of all, what we can notice, like if you add this and this, they will not really come to 0, which means we are missing terms. And the terms that are missing here could be horizontal advection. So it appears that horizontal advection might be really important here. And if you go to föhn, you can see that the dominant balance is actually between the yellow line and the blue line. So the blue line is dissipation, but the yellow line is the vertical transport. And vertical transport didn't play a significant role in Metcrax, but here is the dominant mechanism. So what we have is we are very close to where föhn is blowing full force, and it's transporting kinetic energy from above, where it's developing not in the boundary layer, but in, for example, wave breaking, it's transporting it downwards towards the surface. So if I want to look at the size of the eddies, we can see that it doesn't really look like it did for Metcrax, because for Metcrax, if you remember, katabatic wind had largest scale close to the surface, and then if you normalize it, it kind of all collapsed to one side. And here, for both types of flow, we have small eddies close to the surface and then larger eddies above. And what is interesting here is for this along slope heat flux, which I said was negative here, it's happening at a very large scale. So we have very large eddies that are returning and creating this heat flux. So would we expect scaling to work for this? Here, I didn't separate it into katabatic versus föhn, but this would be the föhn part. It's kind of neutral. And what we can see, so this is again the upper line. This one is the line from flat terrain. The red line is at 6.1 meters, and the blue line is at 1.6 meters. So we can see that it, for these deep föhn flows, it kind of appears to conform to the scaling from flat terrain. And then if you go to katabatic winds, it totally doesn't. Like, under no condition is this similar. So, and it doesn't, yeah?
What's lambda in this?
Oh, sorry, yeah. So this is actually a book of length as well. I'm sorry, I have different notation for the unsimilar figures. So, so this is what it looked like for Metcrax. And what you can see is that it kind of also looks different. So for Metcrax, sorry, okay. So for Metcrax, we had, like for this lower line, we had something that went like almost horizontally straight, which would suggest that eddies do not feel the surface. It's so-called Z-less scaling. And here they have the same shape as our horizontally homogeneous and flat terrain, but they're just like off the line. So the conclusions about the steep slope, we see that katabatic winds that form there have different characteristics than the katabatic winds over low slope angles. We have this very negative heat transport, and what I forgot to say is that the long slope heat flux is like an order of magnitude larger than the slope normal heat flux. So it will be the one that will drive the whole budget. We don't have a balance between shear and dissipation as we normally expect to have, and the eddy size appears to be much larger, closer to the jet maximum than what we would expect. And the scaling just doesn't work the way we want it to work. For the deep flows, we have this vertical transport of turbulence, which is really because you're very close to this very turbulent type of mesoscale flow. And eddies are much larger in size than to katabatic winds, and scaling appears to be working. So if we look at now this shallow slope versus a steep slope, we can say that for the katabatic winds, the slope angle definitely plays a role. We saw that the two katabatic winds are very different. And there were some suggestions that there is a critical slope angle over which this will happen. And it's supposed to be 25 degrees, and we are here at 27, so maybe that explains it. This is still preliminary research, so I don't have the answer, unfortunately. But the downslope windstorm-type flows do kind of look more like what we would expect over flat terrain. But at the same time, we have these two differences. We have föhn winds and the Metcrax winds, and they don't look exactly the same. And I think that this could be, again, I don't have the answer, due to the fact that at Metcrax, we are really far from the mountains, and here we are closer to the mountains. So we are feeling a different type of the flow, which is having an impact on the boundary layer as well. So, okay, so now we know something, what's happening on these slopes, but what does it look like along a slope? And as you remember, we had these 3 additional towers along the slope, and they were quite close together, so I expect my flows to look very similar, or my turbulence structure to look very similar for these 3 stations. And so here I'm showing, just where is this? It keeps disappearing. Okay, so this is the wind speed, the friction velocity, slope normal heat flux, and a long slope heat flux for the 3 stations. So the top, middle, and bottom station, top, middle, and bottom. This is the terrain representation. And the blue line is the katabatic winds. The black line is weak föhn, and the orange line is dark föhn. So the first thing that maybe you'll notice if you look at the light blue line is it's flat. it's pretty flat, which means that along the slope, katabatic wind doesn't really vary. There isn't much heterogeneity in the katabatic wind. It's following the slope, it's doing its thing, and that's it. If you look at the black line, you can see that it doesn't really differ much between the top and the middle. It also looks pretty flat here. But then as you hit the bottom station, all of a sudden, we have a modest increase in wind speed, but we have a high increase in friction velocity. All of a sudden, we have a positive horizontal heat flux and kind of negative slope normal heat flux. So what's happening? We have weak fan winds, and they're impacting the slope, but they're kind of jumping over this part of the slope. There's a separation bubble, and they hit the station here. At the same time, here I can still have similar conditions as if I have katabatic winds. So I could have katabatic winds here and then Föhn just 50 meters down the slope. Yeah.
How do you define strong Föhn versus?
Okay, so strong Föhn was the one where I know Föhn was felt in the entire valley. It was all the way down to the valley bottom. That's how I define it as strong. Versus weak, which when there was a cold pool on the valley bottom, and it didn't penetrate all the way down. Yeah, so it's kind of a random definition. So if you go to strong Föhn, what becomes interesting is that at the top station, it looks pretty much similar as for all the other cases. There is maybe a bit more friction velocity, but nothing significant. At the bottom station, it looks like it's for the weak Föhn. It's again the dots are kind of falling on top of each other. But it's interesting because at the middle station we have no increase in wind speed, but all of a sudden we have a large increase in friction velocity, and we have this positive along slope heat flux, which means that my separation bubble is now kind of around the location of the middle slope. So, middle of the slope. So, depending on how strong the Föhn is, I might feel it or I might not feel it. And if I don't feel it, what I have still are drainage flows. And how do I know that I have drainage flows? So, I can plot this, and Jaylin Sun, if she was here, she would know this. That's her famous hockey stick. So what you do is actually plot wind speed versus friction velocity, for example, or TK or something. And what we expect is as the wind speed decreases, that the turbulence increases as well. So this is what happens at the bottom of the slope. In the middle of the slope, there are two branches. One, we have an increase of friction velocity with increasing wind speed, and the other one, we have a decrease of friction velocity with increasing wind speed, which is totally counterintuitive. Like, how can you have less turbulence when you have stronger winds, right? It should be the opposite. And then at the top station, there is a really significant decrease. And the only reason I can explain this, the only way I can explain this, is if you remember at the katabatic jet, the momentum flux has to be 0, or the friction velocity is very small, which means if my katabatic jet is kind of hitting the station, right? It's going around. At the jet maximum, I have very large wind speed, but very small momentum flux, which means that as this jet maximum gets closer to my station, I have an increase of wind speed, but decrease of friction velocity, which tells me that what I'm experiencing is katabatic winds. So this means that I have katabatic winds at the same time as I have really strong Föhn, only over a distance of 100 meters, which is not a very large distance. So the way I can also explain this is that Föhn is just, because of the separation, it's impacting from a different slope angle. So my katabatic winds will follow the terrain, and my Föhn wind, because it doesn't have to follow the terrain, I mean, of course, it cannot go into the terrain, but it can approach from a different angle. It will kind of overshoot the upper part of the slope, allowing this separation to occur and the drainage flows to continue despite the fact that we have this really strong forcing. And this is what I see if I just plot. So I have my sonic anemometer, and I know, because we do all these rotations with the data, I know what rotation I have to do to get my sonic anemometer coordinate system into the mean flow. So I know, kind of getting out of this, I can get what is the angle at which the flow is impinging on my sonic anemometer. Is it like straight or from an angle? So you can see for katabatic weak winds, where is this cursor? It's like positive and small, and for strong fin, it's very negative. So that means I'm impinging on my sonic anemometer at a much larger angle than when I'm flowing as a katabatic wind. And this can be also kind of shown if we just apply the theory of Baines. So he was looking at flow or hill and looking at the separation that you would expect there, depending on different parameters. One would be like stability times the height of the hill divided by the wind speed, and the other one would be the steepness of the hill. And I know what because my slope is slightly undular, if you remember, so I can calculate these parameters, and I know that it shouldn't really correspond one-to-one, but I can get kind of a feeling of what's happening. And if I plot, so this figure should be representing kind of this part of this regime diagram, and these are all of my data for 11 months of measurements, and these are the ones for which I actually know that there is a separation because I have these 3 stations, and it kind of appears to correlate, right? So I have all of this pink data, which I know there is a separation, and they're all when there is a wind speed above 2 meters, which we have deep flows, and for which all of a sudden we have this separation. So this is not total proof, but it's kind of showing that this is really what could be happening. So to conclude on this heterogeneity, it appears that drainage flows are quite homogeneous. They're just following the slope. They're kind of in equilibrium. They are, nothing exciting is happening. I mean, it is exciting, but nothing along the slope exciting is happening. But then we have firn, and it's very heterogeneous. And the reason why it's heterogeneous is because the flow itself is heterogeneous. We know that downslope windstorms can have separation, can have rotors, can have wave breaking. So there's this forcing which is very heterogeneous, which then translates into heterogeneity on the surface. And then on top of that, we have a non-ideal terrain, which allows additional phenomena to happen, which allows this coexistence of thermally driven flows and dynamically driven flows with very distinct turbulence characteristics over a very short distance. And usually we always assume firn is so strong, downslope windstorms are so strong that they cannot allow the thermally driven flows to survive. They're just like washed away. So coming to what I call the master conclusions, because you already had like 3 sets of conclusions, I can say, which kind of everybody expected, that slope angle plays a significant role, but it plays a more significant role for the flows that are actually determined by the slope angle, because katabatic thermal driven flows are a function of the slope angle. They occur because we have a slope, while dynamically driven flows, I mean, it's just there, right? They come on a slope. They don't care that there is a slope there. So they appear to be more similar to the flat terrain scaling. And I just find it interesting that, as I said, so these thermally driven flows are really different from what you would get in flat terrain. And our models actually use parameterizations developed over flat terrain. So I would expect these flows to be totally wrongly forecasted. But here, going back to the figure I had in the beginning, you see that it kind of looks okay. And then you have these dynamically driven flows, and they shows greater similarity to what you would have over flat terrain, but then they're like totally wrongly forecasted. So this remains as just like a note. There is no further conclusions. And I would like to thank you for your attention with this nice photo from Patagonia, and would be happy to answer any questions.
Questions? Comments? Okay, so I will open, since you opened a little bit of the separation issue. I wasn't sure, you used the diagram from Baines, which looks at the steepness of the slope versus the non-linearity of that. and there are also, when there's stability, there are waves, etc. I wasn't sure what slope you were looking at. The slope of the in valley is 27 degrees, as you told us. So is this the slope associated with a little indentation in the terrain?
Yeah, so like because there are these slight undulations and they have like a height of 3 meters. So like if I just draw a straight line like from here to here, I would kind of, and like turn it horizontal, I would get like little hills. It doesn't really work, but I can pretend that it works. So I get these little hills, and then I can calculate what is the size of these little hills. They're like 3 meters high, and they're like 10 meters wide. So I get my age, and I get my A, like my steepness, and then I just apply. And I know it's really far off. Like I think Mr. Baines, if he knew what I'm doing, wouldn't be very happy.
Who will be here, by the way, next week. So those of you who would like to challenge Mr. Baines on his own diagram.
So I know that it shouldn't really work because, like, first of all, we are in a skewed horizontal coordinate system, so it shouldn't work because of that. We have different force balances and stuff. But it's kind of like a first guess, and just like I wanted to apply it, even though I know it shouldn't work, and just see what I get. And it appears to like give some reasonable results, which would suggest that these undulations play a role in, like, that there might be some separation on these little undulations, and it will be a function of wind speed. So the katabatic winds, which are very slow, they will just flow and like along these bumps and not care. And if it's stronger wind, it will flow over, the same as if you're driving on a wavy road. If you drive faster, you will not feel the bumps anymore.
Okay. So the flow is the katabatic, this wind speed is the katabatic flow, and it's the small indentation in the terrain.
Exactly.
Okay. Any other questions? Comments? Yes?
You mentioned that you rotate your data, anemometer data. Which kind of rotation did you apply?
Okay, so for Metcrax, I used what Anchor gave us, which is planar fit. It's great because you can then also calculate the vertical advections and all this stuff because you have mean vertical wind speed. For iBox, it doesn't work. And it doesn't work for several reasons. First of all, you would have to have different sectors because the flow, it's not an ideal slope. But then the separation is a problem because you have flow impinging. So you have different plane depending on the wind speed. So you would have to have a wind speed dependent planar fit. And I tried to play around with it. I didn't get very far, but we have a paper, me and Matthias, in Boundary Layer, where we are kind of talking about measurements in complex terrain and showing some results. So it appears that double rotation works better most of the time for our data set. But I cannot say that it's universal for any complex terrain measurement. So I think that if your slope is uniform enough, and if it's not too like crazy, and you're not having like these crazy flows, you should be fine with planar fit. And if not, we are not yet there with like the best ever rotation method.
But you can evaluate how much your results depend on the kind of rotation.
Yeah, so we did this not for what I'm showing here. We did this for the 2-year data set, and we saw that if you're looking at the budget, so it depends on what you're looking at. If you look at the budgets, for example, you're looking at energy balance closure, with planar fit, you're getting much lower fluxes than what you're getting with double rotation because part of it ends up being in the mean values. So I think that if for budgeting purposes where you really want to get like all the flux because your energy balance is never closed enough, you need to use double rotation. And then we looked at the scaling and how scaling looks like for planar fit, sectorial, this and that versus double rotation. And it appeared that for this slope, there is less scatter for double rotation than for planar fit. So that would suggest to me that for this particular case, it's better to use double rotation. Yeah.
if no more questions or comments, then let us thank Eva again, and I will encourage you to talk to her afterwards. Thank you.